Hi! In this week we cover the topic of eigenvalues and eigenvectors, which is one of the main topics of linear algebra. You will see that many of the concepts that we discussed earlier, such as the notions of rank, null space and determinant, will play a role in this week's material. Now let's start at the beginning with the following definition. A number lambda is called an eigenvalue of a square matrix A if there exists a non-zero vector x such that A times x is equal to lambda times x. Such a vector x is called an eigenvector of A corresponding to the eigenvalue lambda. Let's have a look at an example. Consider the matrix A and vector x shown here. Let's find out whether or not the vector x is an eigenvector of A. The product of A and x is equal to the vector -2, -6, which is equal to -2 times the original vector x. Hence, the vector x is an eigenvector of A with corresponding eigenvalue -2. Another example, same matrix A, different vector x shown here. Again, we calculate the product of A and x. Now we see that the result is not a scalar multiple of the original vector x. Hence, the vector x is not an eigenvector of A. As you've just witnessed, checking whether a vector is an eigenvector of a given matrix is easy. Is it perhaps just as easy to check whether a number is an eigenvalue of a given matrix? Well, not really. Before illustrating this with an example, let's review the definition of an eigenvalue. Recall the equation A times x is equal to lambda times x. This is of course equivalent to A times x minus lambda times x is equal to the zero factor. By replacing lambda times x by lambda times the identity matrix times x, we can write A minus lambda times I times x is equal to the zero factor. This implies that the definition of an eigenvalue shown here can be rephrased by replacing the condition A times x is equal to lambda times x by the equivalent condition A minus lambda times I times x is equal to the zero factor. This is easier to deal with because it has the familiar form of a homogeneous system, which we know how to solve. Let's have a look at the example shown here. The matrix A minus 2 times I is equal to the matrix 1, 2, 3, 6, which is row equivalent to the echelon matrix 1, 2, 0, 0, which has one non-zero row only, so the rank of A minus 2 times I is equal to 1. This implies that the system A minus 2 times I times x is equal to the zero vector has non-trivial solutions, so we can conclude that the number 2 is an eigenvalue of the matrix A. Now, let's ask the same question for the number 3, for example. The matrix A minus 3 times I is equal to the matrix 0, 2, 3, 5, whose columns are clearly linearly independent, so this matrix has rank 2. Hence, the system A minus 3 times I times x is equal to the zero vector has the trivial solution only. Hence, the number 3 is not an eigenvalue of the matrix A. To round off, let's have another look at our first example. The number 2 is an eigenvalue of the matrix A because there exists at least one non-zero vector x such that A times x is equal to 2 times x. Such a vector is called an eigenvector of A belonging to the eigenvalue 2. Maybe you've already realized that each eigenvalue does in fact have infinitely many corresponding eigenvectors. That observation gives rise to the concept of an eigenspace of a matrix A, which will be the topic of our next video.